Okay folks, so today we're going to be looking at standard integrals, which is the first lesson in the integration topic. Now some of these integrals are on your formula sheet, so if you have that in front of you. So the first one we're going to look at is if we want to integrate the exponential function e to the x with respect to x. Okay. And as you've seen from when you differentiate the exponential, you get the same thing back. Well, that happens with integration as well. So you get e to the x, and then remember you've got a constant plus c from integration. Okay, so that's the sort of basic version of this rule. However, to expand on that, when you have more complicated things in your powers, so if I've got e to the power ax plus b, a and b are just numbers, then because the exponential stays the same, we still get e to the ax plus b, but we differentiate the power. The power would differentiate just to give me a, but because integration, like higher, we divide by that differential, so it becomes 1 over a e to the ax plus b, and we've got our constant plus c. Okay, and that is at the very bottom of your table for your integrals. Okay, that rule there. Okay, so that's the first sort of basic rule. That's the second one there. Okay, we'll look at an example to show you how this will work in practice. So, example 1, let's integrate e to the 3x plus 8 over e to the 2x. Okay, with respect to x. Okay, so that's our first example there. Okay, before I integrate this, I need to put it into the right format. So e to 3x is fine, but here I'm going to have plus 8 e to the negative 2x. I'm going to bring that power up and make it negative 2x so I can integrate it. Okay, so using my rule, okay, so if I integrate that first term, okay, so e to 3x will stay, but if I differentiate 3x, I get a 3, so that gives me 1 over 3 e to 3x. The next one, okay, then I'm going to keep the exponential the same, so it's going to be e to the negative 2x. Differentiate the negative 2x, that gives me negative 2, that comes down and divides 8, so it's going to change the sign to negative 8 over 2 e to the negative 2x plus c. Okay, and again we can tidy up that second expression, so we've got a third e to 3x minus 8 divided by 2 is 4, 4e to the negative 2x plus c. Okay, so that's how integrating the exponentials work. Very similar to differentiation, just because the differential of the power comes 1 over as opposed to just down the front by itself. Okay with that first one? Perfect. Right, so last year at higher, you would not have been able to integrate this next thing, which is 1 over x. Okay, and the reason why is that 1 over x is the same as x to the power negative 1. So if I integrated x to the power negative 1, if you use your rule from higher last year, you would have got x to the power 0 all divided by a 0, and that can't happen. Okay, so that was the only time you couldn't use your rules from higher if it was a power negative 1. So we have a standard formula that if we want to integrate 1 over x, then we get the natural log of x plus c. Okay, that's the rule for integrating 1 over x. Okay, you get a log x plus c, and if you differentiate a log, you get 1 over x. That's what we've seen earlier in the course, so it's just the reverse process. Okay, we'll look at a couple of examples just to show that. However, let's go to the more generic case. If I've got 1 over ax plus b, so the power on the x is still 1 on the bottom, which means negative 1 when it comes up, dx. So that would integrate, so we'd get a log ax plus b, so it's log of what's on the denominator. But then also, if I differentiate the bracket, I get an a, so I get a divided by a, which is 1 over a log ax plus b plus c. Okay, so that's your second standard formula that you see on your table. Now, in your table, it shows you just the top one there, but it'll also put sort of straight lines beside your log x. It just means the exact value, okay? However, you can write it as just natural log x like what I've got here, okay? You won't ever need that other version, okay? So let's look at a couple of examples. So, example 2, let's integrate 1 over x minus 2 dx, okay? So, okay, using my log rules, that becomes log x minus 2. If I differentiate the bracket, I just get a 1. So if I divide by 1, it stays the same. And plus c. Okay, so it's quite a quick, neat rule. Okay, let's look at example 3. Okay, so let's look at 6 over 1 minus 3x. Okay, let's extend my page. Right, what I would do with this question, and it's good practice for a lot of the things you'll see this year, is I would bring that 6 as a constant. So I'm going to bring that 6 out outside the integral, and you can do that if it's a constant. Okay, so that means I'm going to get 6 multiplying the integral. Okay, so if I integrate 1 over 1 minus 3x, so I get log 1 minus 3x. If I differentiate the bracket, I get negative 3, so I get negative a third divided by negative 3, negative a third, plus c. Okay, now c is just a constant anyway, so if I do 6 times negative a third, that gives me negative 2 log 1 minus 3x close bracket plus c. Okay, so it can just help keep the constants a bit tidy and help just keep in check what you're actually doing regarding the integration part. Okay, just keep it more like your formula sheet, just keeping a 1 on the top. Are we okay with that? Right, I'm going to show you another example, but in order to do that, let's recap some rules that you have used a little bit already by doing logarithmic differentiation and using log rules this year so far. But some key rules using logs. So we know log of a times b is the same as log a subtract log b. Okay. We've then also got the rule that if I've got log of a divided by b, that becomes log a subtract b. So I wrote take away b on the top, should be plus b for that first rule. Okay, it's take away for the second one. And then the last one that we've got is log a to the power n. Remember, you can bring the power down to the front. Okay, so those are the 3 rules that we've seen before, but they come up quite a lot today as well. So let's look at an example of when these 3 rules would be required. Okay, so example 4, let's prove that the integral with limit 7 over 2 and a half of 1 over 2x plus 1 dx gives me the value log 2. Okay, so what I prove that we get, if I integrate this with the limits, I get log 2. Okay. Right, so we start at the left hand side. So I'm going to integrate 7 over, with the limit 7 over 2 and a half, 1 over 2x plus 1. Okay, so here we're using our log rules. We've got 1 over 2x plus 1. So we've got log 2x plus 1. But remember, I need to differentiate the bracket, which is 2, so I get a half log 2x plus 1 with the limit 7 over 2 and a half. Okay, so substituting our values in, I'm going to get a half log 2 lots of 7 over 2 plus 1 minus half log 2 lots of a half plus 1. Like that there. Okay, so I've just substituted our two limits in. Okay, let's tidy up the bits in the brackets first. So I'm going to get a half log, okay, well 2 times 7 over 2 is just 7 plus the 1, that's going to be log 8 minus a half log, okay, 2 lots of a half is just 1 plus another 1, I get log 2. Okay, so the next rule we're going to use is the power rule. Okay, so I've got a half at the front of each, I can bring that over and make it powers. Okay, so that's going to be log of 8 to the power of a half, subtract log of 2 to the power of a half. Okay, I can then use the subtraction rule and write it as a quotient, so that becomes log of 8 to the power of a half divided by 2 to the power of a half, like that there. So remember, power of a half means square root, so that means I've got log square root of 8 divided by square root of 2. And using your sud from National 5, the square root of 8 you can split up as square root of 4 times 2, which is 2 root 2, divided by root 2. Root 2's will cancel, so I get 2 over 1, which is just 2, so I get log 2. Okay, so I've proven that I do get log 2 just by using my log rules after I substitute the values in. Okay, so you can be asked a lot of times at advanced higher, to be using a lot of your logs throughout questions, especially integration, because you know you get sort of two parts when you put in limits. Okay, are we okay with that example there, folks? Yeah. Right, I'm going to show you just another couple of quick rules, and then we'll get you on your worksheet. So this first one is on your formula sheet. Okay, and again, it's the opposite of what happens when you differentiate. So if you want to integrate sec squared x dx, then you get tan x plus c, okay, which is on your formula sheet. And again, a more general version of it is if I've got sec squared bracket ax plus b dx. Okay, so I'm going to get tan ax plus b. If I differentiate the bracket, I get an a, so I get 1 over a tan ax plus b to the power c. Okay, so that's the more generic rule there. Quick example, if I want to integrate sec squared 2x, then I get, well, differentiate the bracket 2, so I get a half tan 2x plus c. So you can see it's very similar to the rules that you've done for sin and cos at higher that you need to remember this year. You've got this one in your formula sheet just because it's a new function, but it works the same way, okay? Differentiate in the bracket, becomes a fraction of it, and then you just swap it for what it becomes in your formula sheet, remember plus c as well. We okay with that one there? Right, the very last one, which is not on your formula sheet, which is quite a powerful rule actually, is the rule, if you've got an integral and you've got a quotient, which we know means divide, and it has the property that the function on the top is the differential of the function on the bottom, okay, then you just get log of the function that the original was, the denominator, okay, plus c. Okay, so if it's got a special property that the differential of the function's the numerator, and the function on the bottom is the denominator is the original function, then you just get log of that original function. Okay, we'll look at a few examples just to show you how sometimes it might not look you've got that, but you can manipulate it to get it to look like that. And I'll show you what I mean just by a few examples. So if I go to example 6, just show you the quick rule first. So if I want to integrate 2x over x squared plus 2, which is something you couldn't have done last year. Right, well, let's check the property. So if x squared plus 2 is my original function, if I differentiate x squared plus 2, I do get 2x, which is my numerator. So I've got that property, therefore my answer can just become log of x squared plus 2 plus c. Okay, just because I've got that property. If I then go to example 7, so this is an example of where it might not seem like you've got it. Okay. Okay, so if I wanted to integrate x squared over 3x cubed plus 3, okay, so you can see that this isn't exactly that format, because if I look at my denominator, which is 3x cubed plus 3, if I differentiate that, well, I get 9x squared, don't I? Now, that means I should have 9x squared on the top, and I don't have 9x squared on the top, I've just got x squared. So I'm really close to what it is, but I can manipulate this. As long as I keep the question the same, I can make it look like this. So how I can do this? Well, it'd ideally be nice if I did have a 9x squared on the top. Okay, so I've multiplied that numerator by 9. But if I multiply a numerator by 9, that means I need to multiply a denominator by 9 to keep it the same, because 9 over 9 would be 1. So how I can do that is take a ninth of it all. Okay. Oh, good spot, good spot. Yep, it should be plus. Sorry, it should be plus. Thank you. Yeah, so do you see how I've made it the same question still? Yeah, I've just times the top basically by 9, so I've got 9x squared, and I've also taken a ninth of it all, so that I'm cancelling that 9 out, but I'm keeping a ninth out so that I've got this property here. So therefore, I get a ninth. Okay, so if I integrate this, I get log 3x cubed plus c. Are we okay with that example there? So that's a version of a question where you're very close to having one of these rules, and you can just manipulate it slightly so that you get that, and it becomes a lot easier to integrate it. Okay, we all good with that? Right, the very last one I want to show you, this is the last one, I'll do a long video. I want you to think about this one. So, right, tan x. Unless you've read something that I don't know you have, there's probably not a way you would know how to integrate tan x. Okay, it wasn't one of the ones that you done last year, and it's not on your formula sheet. We can integrate sec squared and get tan, but we don't know how to integrate tan. Okay. However, if I remember what tan is, then tan is sine over cos. Okay. Now we know what can happen to sine and cos. They interchange when you integrate and differentiate them. So if cos is my original function, my f of x, and I differentiate cos, well, we know cos normally becomes negative sine x. So again, I'm very close to having what I should have on the top, but I want negative sine x. Therefore, I can put a negative out the front and change that sine x to negative sine x. That way both negatives would cancel, get back to what I have. And that way now I do have the differential of cos on the top. So I get negative log cos x dx. Okay, and that's how you would integrate tan. We all good with that? Okay.